This is the screencast for section 2.3, example 1. We're going to look at continuity. Continuity is the tie-in between a limit of a function and the function's actual value. So as you saw in the last section, a limit can exist without that function being defined there. However, when the limit as x approaches c equals the function's y value at c, the function is continuous. We also have continuous as a right endpoint and continuous as a left endpoint. So the limit as x approaches a from the right equals the y value there, or the limit as x approaches b from the left and equals the y value there. Continuous as a left endpoint, continuous as a right endpoint. So let's look at some examples. This first picture you see here, the limit as x approaches 0 is 1. And the function's value at 0, so the point actually exists at 1, therefore f is continuous. This next picture, the limit as x approaches 0 is 1, but f of 0 does not exist. So f of x is not continuous at x equals 0. I would have to pick up my pencil to continue drawing this graph. In the third picture, the limit as x approaches 0 is still 1. F of 0 in this case does exist, however, the function's value is defined at 2. So f of x is not continuous at x equals 0. So there's a look at some removable discontinuities. Now let's look at some infinite discontinuities or jumps. In this jump discontinuity, the limit as x approaches 0 from the right is 1. The limit as x approaches 0 from the left is 0. The function is actually defined at 0 to be 1. So this function is not continuous in general here. It is only continuous as a left endpoint. The limit as x approaches 0 from the right and the function's value are the same, so that is a left endpoint of the function, of that piece of the function. This next picture is an infinite discontinuity. The limit as x approaches 0 from both sides, so the two-sided limit is positive infinity. F of 0 does not exist. So since the limit as x approaches 0 does not equal f's value at 0, the function f of x is not continuous at x equals 0. Now this is something you haven't seen before. It's called an oscillating discontinuity. Basically, the limit as x approaches 0 does not exist in this case because the period is getting infinitely small as you approach 0 for this function that is oscillating between -1 and 1. So the limit as x approaches 0 does not exist. And f of 0 also does not exist, so there's no way this is continuous at x equals 0. So example 1 gives us the opportunity to look at one graph and a bunch of different points on it to talk about its continuity. So let's start from left to right. Let's look at x equals 0 first. The function doesn't approach 0 from the left, so let's just look at the limit of f of x as x approaches 0 from the right. That's going to be 1. F of 0 is also 1. Therefore, f of x is continuous at x equals 0 as a left endpoint. Now let's look at x equals 1. The limit as x approaches 1 from the left is 0. The limit as x approaches 1 from the right is 1. And f of 1's value is 1. So the function isn't continuous at x equals 1, but it is continuous at x equals 1 as a left endpoint. At x equals 2, the limit as x approaches 2 from both sides, so the two-sided limit is 1. The function is defined at 2 to be 2. So since their limit doesn't exist the actual function's value, doesn't equal the function's value, this function is not continuous at x equals 2. Now 3, the limit as x approaches 3 from both sides, so the two-sided limit is 2, and f is defined at 3 to also be 2. So therefore, f of x is continuous at x equals 3. And finally at 4, there is no function to the right of 4, so we'll just look at the limit as x approaches 4 from the left, and that would be 1. F of 4 is also defined to be 1. The function's actual value there is 1. So f of x is continuous at 4 as a right endpoint. Now try problem number 5. Says find the points of continuity and the points of discontinuity of the function. Identify each type of discontinuity. Now I could graph this in my calculator, but from our experience in pre-calc, I know that this is a square root function that should have started out at x equals 0, but now is going to start out left 1.5. So negative 3/2 comma 0, and is going to go up from there. In other words, if I plug in negative 3/2 for x and then add 3/2, I get 0, which is the left endpoint of this function. Speaking of a left endpoint, the limit as x approaches negative 3/2 from the right of y is 0, which is also f of negative 3/2. Therefore, y is continuous as a left endpoint at x equals negative 3/2. Y is continuous everywhere else greater than negative 3/2. So I'm going to say let c be an element in the interval not including negative 3/2 to infinity. The limit as x approaches c of y equals f of c. Therefore, y is continuous for all c.